Let's start with the class, which is here. So we are now up to 9:18. So it's chapter 4, Block Ciphers today. And let's talk about them. This is really important. This is what almost everybody uses all the time. The main one being AES. It is the norm. When you just say you're encrypting something, almost always you mean you're encrypting it with AES. It is the normal all-purpose cipher, and we're going to talk about how it works. So originally, the United States defined a federal standard for the data encryption standard, and that was the official recommendation from 1979 to 2005. And this is, as I mentioned many times in this course, a lot of the crypto wars come from this because it was known to be spectacularly insecure by the 90s, and they continue to be the official government recommendation. So this is unfortunately a repeating pattern that the US government tells people to use something that is not safe. That's why a lot of the cryptographers become pretty anti-government, revolutionary sort of people that criticize the government greatly and prefer to use things that are not approved by the government. So anyway, they eventually admitted we couldn't keep using DES, which I understand was because of European pressure. The Europeans said they were not going to let Europeans put their money in American banks if we were not going to secure our stuff with proper encryption. That's what I heard. I don't know if that's the real reason, but certainly that sounds about right. I know that's what's happening with our privacy laws. The only reason we have any privacy laws is because of European pressure. So the Europeans are not as productive at creating new things as we are, but they're much more interested in regulating things with the government, and their regulations are, that's their contribution lately. Anyway, the KGB had their own system called GOST. Anyway, so in 2000, they had a contest around 2000, and in 2000, the National Institute of Standards selected a Belgian cryptographic system, and called it AES. It was originally called Ringale, I think that's the name of the person that wrote it, and they anointed it and defined it as the advanced encryption standard to replace the data encryption standard. And it has been the standard since 2000, and as far as anybody knows, unlike DES, there's nothing wrong with it. It seems to be completely secure, people quite trustworthy, and it's good that people are using it. Now, it's a block cipher, and so a block cipher works like this. You have an encryption algorithm and a key, and then so you take a block of plain text, encrypt it with the key, and that creates a block of ciphertext, and then you decrypt it with the decryption algorithm with the key to get back to the plain text, just what you'd think. So the security goals are the block cipher should be a pseudo-random permutation. The encrypted data should look like just a random pattern of bits. The attacker should not be able to compute any encryption without the key, and there should be no patterns they can find that they can use to deduce information about the key. DES used a block size of 64 bits. AES uses a block size of 128 bits. These are chosen to fit in the registers of CPUs. You might have a 64-bit processor, and so multiples of 64 is good. And you can't use smaller block sizes. Block sizes below 64 would be vulnerable to a codebook attack. Suppose you had a Wi-Fi network where you can send up arbitrary data and it will encrypt it for you, but you don't know the key. Well, then all you have to do is encrypt every possible plain text, record them, make a codebook, and now you can just look up blocks of ciphertext in the codebook. So if you don't have a big enough block size, you're vulnerable to this attack. Now, if you had a block size of 32 bits, that would only take there would only be 2 to 32 possible blocks, and that's only 4 billion, and storing 4 billion things in a database is not difficult anymore, so 32 bits is never going to be secure. 64 requires 2 to the 64 entries, and 2 to the 64 bytes of RAM is too much to buy and too much to use, so 64 or larger should be good enough for block size. And like I say, it used to be 64, now we're using 128, which is fine. So the block size is all right. So now we got to talk about how to construct the cipher. Now there's two techniques, substitution, permutation, and Feistel. And whatever you do, you define a technique of encrypting it, and then you usually go through many rounds. Encrypt it again, encrypt it again. That's how you typically do it. So if you encrypt it with 3 rounds, when you decrypt it, you have to decrypt it with 3 rounds, and you decrypt it in reverse order. First with the round 3 decryption, then with the round 2, the inverse of round 1, as you might imagine. All right. So the round functions use the same algorithm but a different round key. The round keys are derived from the main key using a key schedule that somehow derives a series of keys from the starting key. And so if you didn't use a key schedule, and if you used the same key every time, then you'd be vulnerable to the slide attack. So suppose you had 3 rounds. Here's plain text 1. Your first round turns it into this partially encrypted stuff, P2, and eventually into the fully encrypted stuff, C1. But if you are able to find plain text blocks with P2 equal this P2, then you'd be able to deduce the key, because that implies that this cipher 2 is related to that cipher 1 by 1 round. You know, the point is you're able to take this thing where you really should be only analyzing all 3 rounds together, and the slide attack lets you break it down to being analyzing just 1 round at a time. And as we've said before, it's usually much easier to break 1 round. That's why you do multiple rounds. 1 round doesn't really make it strong enough. You do multiple rounds, and you don't want the attacker to be able to reduce the mathematics down to doing 1 round at a time. All right. Let's see, I've got a comment coming in the Twitch. If you use the same seed and get the same output from a pseudo-random generator, then it's not random, is it? Well, technically what it is predictable in that case. It still could be pseudo-random, and that's true of a lot of them, where if you give it the same seed, that's why you have to define what you mean by random. It is predictable from the seed, but that's generally the case. All right, and we talked last time about some of the properties. All right, so that's the slide attack. So the solution is all the round keys should be different. You should use a different key every time, and now you can't slide it down here and break out just one section. Now, one weakness, by the way, in AES is that the key schedule is not one way. So if the attacker is somehow able to find out one round key, they can deduce the master key from that. So if they had a side channel attack, like measuring electromagnetic emanations that revealed a round key, that would reveal the main key. So that is one property of AES that is not perfect. It has not turned out to be a big problem in practice, but in principle, that's a weakness. All right, so in a substitution permutation network, what you want is you want confusion and diffusion. Confusion means that several bits of the key are involved in each ciphertext bit. And diffusion means changing one bit of plain text will change many bits in the ciphertext, and this is the point. You shouldn't be able to make, like you could put in 2 plain texts that are only different by 1 bit, and then try to analyze the difference in the ciphertext, and what you should find is just random changes all over, not anything that makes it easy to focus on a part of the process and deduce information about the key. All right, and then there's Feistel schemes, and the way these work is you only have a Feistel function, and you split the input block into 2 halves, and you only encrypt 1 half. Then you move it over here and XOR it, then you encrypt and flip them. Then you can encrypt this half. So each round only encrypts half the data and mixes them together, and then you do this over and over. So the DES used 16 Feistel rounds. There's nothing terrible about encrypting just half every time. That's just how it works. That's the Feistel system. All right. So let's try a Cahoot. Let me bring those up here. Yes. All right. This is 141.4a. so what kind of rounds are used in AES? That's substitution permutation. We're going to see more details about it soon. All right, what attack cracks ciphers with small block size? That's the codebook attack. You just put in every possible block and record their output. All right, what attack cracks ciphers with fixed round keys? Slide attack, you have a special condition where you compare the first round of one encryption and the last round of another encryption, and that way you're able to break the multi-round process down to just one round to analyze it. All right, what kind of rounds encrypt only half the plain text? That's the Feistel rounds. All right. Switching. There we go. I think I saw another comment in the Twitch, which is over here. There. How much weaker is the half Feistel system than encrypting both sides at each round? Well, I don't know, but I would imagine it would take 2 rounds of Feistel to be about the same as 1 round of AES, but I'm only guessing. I haven't seen a mathematical study. I'm sure there are subtleties and details. All right. So let's talk about AES. DES had a 56-bit key, which of course was cracked by brute force in 1997, and there was a lot of clues before that it wasn't going to be strong enough. That's not a big enough key. I mean, 2 to the 40 is not an impossible number, and 2 to the 56 is not impossible either. So if you can use 3 rounds of DES using 2 or 3 different keys, that's triple DES, and that's much stronger. And by the way, it's strong enough to be essentially unbreakable. It has a cryptographic strength of 112 bits, so it's perfectly fine. If you're using triple DES, that's okay, but it turns out it's slower than AES. It's less optimized for the processor, so there isn't much reason to do it. The only reason anybody ever used triple DES was for backward compatibility with hardware that was still running DES. So AES is the replacement, and that's been the NIST standard since 2000. So let's take a look at this video and see what AES does in general terms. Let me go to my 140, let's see, I'll probably use Opera. Let's see if it works. If I do 4A, there it is. Okay, here's a visualization of the Rind jail cipher. The most common version of 128 bits. So your plain text is coming in, and you got ciphertext coming out. So there's a state and a key, the 128 bits long, which is 16 hexadecimal bytes. And so there are steps. Here's the encryption process. You go through 9 rounds of these 4 steps, and the 10th round is missing one of the steps. So here's the transformations. You substitute bytes. Let me it's going a little too fast. Let me stop it here. If I can get it to stop there. You substitute bytes. Hey, I'm trying to get it to stop, and I'm not having any luck. All right, there. So you substitute bytes, you shift rows, you mix the columns, and then you add the round key. Those are the 4 steps. So, all right. This is substituting bytes. You have the input here, which is your 16 bytes, and you just look them up in this S box, which is a table with numbers that look at pretty much random. You use the 2 hexadecimal bytes, the first one as the column or row, and the other one is the row or column. So you just look it up. 19 takes you to this number. That's substituting each byte with bytes looked up in the magic S box, which is chosen to scramble the data. Then you shift the rows. Now the point is, if you think about preparing food where you're trying to make hash, you're cutting up potatoes or something, you cut them up this way, you cut them up that way, you stir them up, you're trying to scramble the bits to get rid of all the patterns. So to get rid of vertical stripes, you do this operation, which mixes things together. So if there was some kind of pattern vertically, you just scrambled it. That prevents one type of pattern. Then you're going to do another shift where you mix columns just to combine it the other way. So you're going to take each column and multiply it by this matrix, which is going to scramble it this way. So if there was a horizontal pattern, like these are all the same rows, this will scramble it vertically. That's just like you would with food. You cut it up this way, you cut it up that way to scramble it up. So that's going to scramble it this way. And finally, you add the round key, which is just there to make sure that all the rounds are different, to avoid that attack, the slide attack. So you just combine it with the round key with XOR, and the round key is just created with a simple operation to create all these round keys. And that's just to make sure each round is different, and of course that the key is used somewhere. So that's the game. Those are the 4 transformations you use, and these transformations are chosen to create the mixing of all the bits that you want, to incorporate the key, so the key matters, and also they're chosen to be fast and efficient on processors. You don't do anything that a processor can't easily do, so it'll be cheap to implement hardware that applies this. So there's your rounds, do all the 4 steps. And you skip one step on the last one. For some reason, you skip the mixed columns. And that gives you your ciphertext. And the key schedule takes your key and it generates a whole bunch of keys from it. And they're doing it, rotating words, then they're using the S box again. That's how they're doing the transformation to take the one key and turn it into all these round keys. And this is not random at all. It's just if you know the key, you can predict all the round keys from it. And as they say, a weakness is if you know even one round key, you can reverse this and get back to the main key. It's not supposed to be a secret or weak. It's just a way to create a different key for each round. So you can't do that sliding attack. All right. So that's what I wanted to show you. I think there's nothing more exciting here. To get the general structure of how this is going to work. And let me check to see if there are comments coming in. Okay, no more new ones. All right, so that's an overview of the system. All right, so here's the internal state of the AES is a 4x4 array of 16 bytes. And so here's the steps we talked about. You add the round key, substitute bytes, shift rows, mix columns, add the round key, and you do this a bunch more times. And out here comes the key schedule, key expansion, where you've taken the original key and you've turned it into all these round keys, K0 through K10. All right. So without the key expansion, all rounds would use the same key and be vulnerable to slide attacks, where you compare the first round with the last round of a different encryption. When you didn't have add round key, it wouldn't depend on the key at all, and therefore you'd just have a transformation without a key anybody could get in. Substitute bytes is a nonlinear operation where you're just looking up things in that table, so it's not mathematically linear at all. It's basically random, and that means you don't have a system of linear equations that can be solved using standard algebra techniques. Without shift rows, changes in a given column would never affect the other column, so you could decrypt each column separately, and that would break it down to 32-bit ciphers instead of 128 bits, and that's bad. That would make you don't ever want to let the attacker break the problem up into a smaller problem. And without mixed columns, a change in a byte would not affect any other bytes, and so you'd be able to decrypt the bytes one by one. So that's the point. You're trying to mix all the data in every way, so that there's no way for an attacker to break this into chunks and attack the chunks one by one. And you can implement it in Python 3 very easily. And one thing, it's probably worth doing this because one thing it shows you is the importance of padding. So let me take this stuff, which I would like to copy. I'm getting some kind of grief out of my slides here. There we go. All right, let's see if I can do it. If I clear, all right, and I go to say Python 3. Let's see if I can do this stuff. I encrypt it, import AES. Okay, then I make a key. Then I choose the simplest mode, electronic codebook, which is also called textbook encryption. So here's my message, hello from AES with 2 exclamation points. And I encrypt it, and so it turns into this random junk. And that's my ciphertext, and I can decrypt the ciphertext and get back to this. Now, if I was to try different plain text, if I go back to my A, and I get rid of one of these exclamation points to make it a different length. Now, if I try to encrypt it, ciphertext is cipher encrypt, and it won't let me do it. Data must be aligned to block boundary. What they're telling you, it must be 16 bytes, or 32 bytes, or 48 bytes. You have to fill the block. And this is chosen to be just 16 characters long. So hello, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That's why I need 2 exclamation points at the end to make it 16 bytes long. You have to fill the block, which is going to turn out to be a big problem. All right, so if you want to make it faster, you can implement each of these steps as a separate function in some language like C or Python, but if you did that, that would be pretty slow. You keep calling the function over and over. It turns out that making a table to implement these functions and just looking them up is much faster. So here's an example of how OpenSSL does it. It's table-based. It just looks up in table 0 something and table 1 and table 2 and table 3. It looks up all the pieces by taking some kind of input and just shifting it around bitwise to choose what part of the table to look up. This is a way to make it really fast. Pre-compute as much as you can and look up everything in a table while you're doing the encryption or the decryption. Now the problem is, if you do it that way in software with table lookups, it turns out that especially if you implement it with functions, I'm not so sure about table lookups, but I think that's still true. For example, if you're multiplying by 0, your compiler of your language will automatically do that really fast. It will just set the answer to 0. But if you're multiplying by some other number, it will go through a multiplication process with a lot of steps. So if you write it in some language like C, and then you compile it, the compiler optimization will cause it to give you a timing attack vulnerability. It will take a different amount of time to encrypt with some keys than others. As you might imagine, a key that's all zeros will probably go really fast. So this means if you measure timing, you leak information about the key, and that's a problem with any efficient coding. So one solution is to use constant time programming, where you carefully use inefficient code that will always go through every step, even if it doesn't need to, like you're just multiplying by a series of zeros. That's one way, but a better solution is to write hardware. It's to build it in the hardware, and that's what happens. Almost everybody has hardware-based AEI now. And what you do, you're already used to the fact in hardware, you feed in the input data, you feed in the command, it just goes through the stages, it comes out in just a fixed number of clock cycles. It doesn't depend on the data coming in or the data going out, how long it takes to do an integer multiplication or anything in hardware. It just goes through the steps. So you give it AES commands, and that's the thing. And this turns out, of course, to make it much faster also. So it makes it about 10 times faster than implementing it in code, and it also makes it timing independent. This is what almost everybody does now. Every processor pretty much includes AES code because we use it all the time. So AES has many good design principles. It resists many attacks. Of course, you never can say it's going to be good forever, but it has stood for more than 20 years, and nobody's found a significant weakness. The only weakness is the one I mentioned before. In theory, if we had good quantum computers, they could crack AES 128 in only 2 to the 64 operations, so we'd have to move up to AES 256, which already exists. We won't have to go any further than that, though, for any of the attacks that are understood to exist right now. And that attack is purely theoretical, because the quantum computers are nowhere near good enough to do it yet. But now we got a problem about the padding. Now the simplest one is electronic codebook. You just encode each block of plain text with the same key, and that's it. Now the problem with this is if you have another block of plain text that is equal to the first one, you'll get the same output. So it doesn't really remove all the patterns in the data. This is why this is called textbook encryption. This is what amateurs do that take a math course and they don't really study programming. They do this, which is encrypting with the key, but it's encrypting in a way that is not going to be good because it can leave patterns in the output. So if I have this dead men tell no, dead men tell no, and I encrypt it, let me just do it here. If I change this and then I put that in again, let's see if I can do it with copy and paste. I think I can. There. If I encrypt it with your 2 repeated lines, and now do encrypt ciphertext. Okay. Oh, I'm missing the extra exclamation point at the end. All right. Now I should be able to encrypt it. There we are. And so I should be able to print the ciphertext. There. And there it is. And now, notice this 5930, and here's the other 5930. And so, as I've done before, you can just change the width of the screen, and there you go. So you can see, if I encrypt 2 16-bit character strings, and then I encrypt another one, they come out exactly the same. This is not good. If there's a pattern in the input, some patterns are preserved in the output. It didn't really hide that fact. So that's a problem with electronic codebook. All right, and I found this to be true of a lot of things. Like I say, Android apps are part of what motivated me to write this course. The Staples Android app, for example, encrypts your password and stores it locally. So I just made a password that had 32 A's and then some other characters to meet their complexity rules. And when I looked at what they stored, it was in base 64 here. And when I unbase 64, the same thing happened. The first 16 bytes repeat as the next 16 bytes. So this is the first 16 A's. This is the next 16 A's. So that means they're using electronic codebook mode, which is one of the many mistakes they make. And like I say, Android apps are garbage. They're obviously written by people that don't know anything about encryption, and they just read like a blog post and did the simplest thing, and neither they nor their bosses know enough to properly audit their encryption techniques. By the way, the other fundamental problem with AES is it's got a secret key, and you have to hide the key somewhere. Hiding the key in an Android app when I can see your source code is a futile exercise. So that's another serious flaw. Anyway, all right. So you can do this here. I think I did this one. Didn't I demonstrate this one in this class? Maybe not. We'll do it in the projects later. But so if you encrypt an image, and the image is not in a compressed format like ping, but it's in a bitmap, then this gray area is just 16 bytes of gray and another 16 bytes of gray and another 16 bytes of gray. So when you encrypt it, it's just each of those blocks is going to turn into the same thing. So you can still see the penguin. You know, it doesn't. Large-scale features are not removed by encryption. Now, this is not what you expect encryption to do. The point of encryption is it should scramble stuff so you can't see it at all. And that's not what happens. So the solution that was recommended for this was cipher block chaining. You would include an initialization vector in addition to the key. You take the IV and you XOR it with the plain text and encrypt this first block. Then you take the ciphertext here as the initialization vector for the next block. And this way, even if the second plain text is equal to the first plain text, the IV will be different, so you'll get different output. And the IV is not a secret. It's sent in the clear along with the ciphertext. You send the ciphertext and the IV so that the person can decrypt it, because they don't give them the key, and so this has a much better result. Now, if you encrypt that, it turns into just random snow, which is what you want. When you encrypt something, the idea is it should be totally hidden. All right, so that was the recommended system for a long time, and it's better than the electronic codebook. Now, if you use the same IV again, then you've got a problem. If I encrypt another image with the same IV, well, then the first block is going to encrypt with exactly the same key stream, the same. So that's a weakness. You should not reuse the IVs. All right, with the same. If the first plain text block is the same and the IV is the same, they'll have identical ciphertext, so you have a small amount of the same weakness if you reuse the IV. Now, here's another consideration. You can do this on a parallel computer. I could have a GPU or something with a lot of processors. Each of these calculations is completely independent, so I could get a speed up from the massive parallelism of GPUs and multi-core processors, which is cool. But this one, I can't. I have to do block 1 before I can do block 2. I have to do block 2 before I can do block 3. This is a single processor threading through, so that's not efficient on a modern processor. So that's a problem. You cannot do it in parallel. It requires serial processing. All right, now here's another problem. Like I just showed you, if you try to encrypt something that is not 16 bytes long, it will refuse. So that means if you want to encrypt messages that are not 16 bytes long or a multiple of 16, you have to pad them. And here's the padding system that is normally used. If you need 1 byte of padding, add a hexadecimal 1. If you need 2 bytes, put 2, 2. If you need 3 bytes, put 3, 3, 3. If you don't need any padding, then pad an entire block of 16 characters, each 16, which is 10 in hexadecimal. And the point of this, of course, is it makes everything the right length, and it makes it easy to remove the padding. When you're done decrypting it, you take the last byte, and then you throw away that many bytes. And now you get the original message. You managed to have an easy way to get rid of the padding. So that's what's done. So the problem is, see, almost everything uses this padding. But if you are able to feed in data, and it warns you when you have a padding error, that addition, instead of just telling you, I can't decrypt it, or giving you garbage, it warns you that you have a padding error. If I can detect when the padding is incorrect, that's enough to shatter the whole thing like glass. Remember, if you used a one-time pad twice, it shattered like glass and became insecure. The same thing happens here. That little bit of extra information is enough to ruin the whole thing, and we'll do it in the projects. Now, I see another comment in the Twitch. This is just spam. All right. All right, so there's an alternative to padding, by the way, where you pad with zeros and you swap the last 2 blocks of ciphertext and discard extra bytes at the end. Is a little confusing. Somehow you mix the last 2 blocks with padding of 0. This is called ciphertext stealing, and it's considered quite secure, but it's sort of confusing and hard to program, and nobody ever uses it. It is better than that PKS number 7, PKCS number 7, but very rarely used. That's one option. This is what's recommended, is counter mode. And by the way, in particular, the most recommended procedure now is Galois counter mode. Counter mode works like this. Instead of taking the output of one block as the IV for the next block, you just use a counter. You create a counter value 1, counter value 2, counter value 3 according to some schedule, and then you use those for the IVs. So the result is now you can do it in parallel. These are all predictable, and as long as you don't repeat any of these nonces that go in, then it's quite secure. And this is considered the most secure, best way. There is no connection between one byte and the next byte. So you have a different nonce for each message, and all right, the nonce must not be reused. And so if you were to use the same nonce and the same key, then of course you'd have the same bit stream to encrypt things with. By the way, notice something here. The way you do it, you take the nonce and the key, and you run it through this function, and that creates a pseudo-random bit stream. Then you just XOR the plaintext with the ciphertext. So there's no issue of padding. This is creating a pseudo-random bit stream, which you're just XORing with blocks of plaintext. So if there's not 16 bytes of plaintext, it doesn't matter. You just XOR the bytes you have. So this is like the one-time pad, which is why I said before, the one-time pad would be the perfect system, and all the other systems imitate it. This imitates it. You have this series, you take your first nonce value, and you create 16 bytes of apparently random stuff. Then you take the next nonce, you get another 16 bytes of nearly random stuff. You have a long stream of effectively random bits here. That's your one-time pad. It's not a perfect one-time pad, though, because you generated it from one key and from a schedule of nonces. But it's very close, and now you just XOR that with the input data to get the output, and you invert it the same way. So you could even pre-compute that key stream, because it doesn't require the message. You could pre-compute it just like a one-time pad and have it ready to go, and then just XOR the plaintext with the ciphertext to encrypt it, and XOR it to decrypt it. So as long as you know the pattern, this is a good mission. This is the most recommended way to do it now, rather than cipher block chaining. Padding doesn't matter. This is now a stream cipher. you've taken a block cipher and turned it into a stream cipher. You calculate blocks of a key stream at a time, but you can use them like a stream, so it's pretty cool. Has the advantages of a stream cipher. All right, and you can parallelize it, like I say, faster than any other mode, although I think they must not be considering electronic codebook. That would seem like that would have to be even faster because you don't even have the IV. But anyway, very fast. All right, and so we should talk about how things can go wrong. And let me just check and see if there's more comments to answer here. I see something going by. Yeah, Galois. Yep, Galois, one of the mathematicians, absolutely. And at least my students corrected me in pronouncing the name. It's French, it's not Galois. Apparently it's Galois. Like, I know nothing about French. Anyway, and I don't know much about it, except he invented a function to create those pseudo-random nonces, which is considered a good choice. You don't want to use a random number for the nonce, by the way. If you used a random number, then it'd have a high chance of using the same nonce before long. So you want a series of non-repeating numbers. So it will never repeat in the time of your message. All right, so here's things that can go wrong. There are two basic attacks. The first one is meet in the middle, and this explains why we have triple des. I wonder why we don't use two des. Well, suppose you use 3 different keys. That would be the easiest way to do it. So suppose you just encrypt with the key. Now, the way they actually do it, you then decrypt with key 2 and encrypt with key 3, but you could encrypt 3 times, and that would be fine too. This is triple des. Now, the reason you don't use double des is this, the meet in the middle attack. Consider 2 des, where I just encrypt, and then I encrypt here. If I could take the ciphertext and decrypt it with key, and I could take this and encrypt it with a key. So what I do, now in principle you think, I need 2 56-bit keys, 112 bits. If this are 212 calculations, then I could never get in. So if I tried to crack it by guessing K1 and K2, I'd need 56 bits of K1 and another 56 bits of K2. I'd have to do 2 to the 112 calculations to crack it. But there's a better way to do it. You meet in the middle. What you do is I know the plain text and I get a ciphertext. Now I want to find K1 and K2. So what I do is first, I encrypt 1 round with K1, and I do that for all possible values of K1, which is only 2 to the 56 values, and I make a list of all those. So I need enough time to do 2 to the 56 calculations, and I need enough storage to store 2 to the 56 results. But neither of those is impossible. Now I make a list decrypting here for all possible keys. Now I just find the one that is identical in the middle, and now I know K1 and K2. I just look it up. So this turns out I only have to do 2 to the 57 computations to crack it, because I can do half and then the other half, instead of having to do it all at once. This is why when we talked about AES, they may make sure you can't break the rows out alone or the cells out alone, because if you could, it would be easy to crack. You don't want to be possible to break it into smaller problems. You want to force them to solve the whole problem all at once. And then it will take 2 to the 128 calculations, which is too many. And this one does not really force you to solve the whole thing all at once. You can solve this half and this half separately. And that's the meet in the middle attack. So that's why I use triple des, because even if you try to meet in the middle, you can do 1 round here, but you have to do 2 rounds of decryption, or you can do 2 rounds here. Either way you cut it, one of those steps involves having to do 2 keys at once, and that's 112 bits. That explains why it only has 112 bits of security, not 3 times 56, but 2 times 56. However, like I say, in practice, it's perfectly fine. Triple des is secure enough. If you're using it, there's no reason to panic and go to AES. It's fine. 112 is enough, but it's just out of date, and you should probably update your stuff to use AES. But if you got some old stuff running triple des, there's nothing to panic about it. All right. And so let's talk about the padding oracle attack, and we'll do this in the projects, but here's how it works. You have, you're going to encrypt something. Suppose you're encrypting something that's only 47 bytes long. So you got 16 bytes, another 16 bytes, and here you got 16 bytes, but the last one is empty. So it's going to pad it. It's going to have to put a 1 byte of padding here. Then you add an initialization vector, encrypt it. Then you take the ciphertext here as the initialization vector for the next block. You take the ciphertext here as the initialization vector of the next block. Now, as soon as I heard about this, I knew this was dangerous and something wrong, because you take the output of one process and use it as the input for the next, and you do it in a very simple way with just an XOR operation. This seems really unwise, to tie one block to the previous block with a simple invertible operation, and that does turn out to be fatal. And it's easier to see on the decryption step. So in the decryption step, I feed in 16 bytes of ciphertext, I decrypt it with the key, then I XOR it with the initialization vector to make plain text. Then the next time I take this ciphertext and it's the IV. So I decrypt this and put the IV there. And here I decrypt this and put the IV there. And the problem is I've got this 1 byte of padding here. Now what you do, you change the last byte in this block. This is the attack. So I change this last byte just to something random. So the ciphertext is now invalid. That is going to create collateral damage. I'm going to scramble all this whole block of plain text into garbage. But what effect will it have on the next block? The ciphertext is used as the IV and XOR'd here. It's only going to change 1 byte of the next block. Now remember, we talked about this. If there's any way for a change in the input to only make a localized change in the output, that's bad. That means you'll be able to focus on a small part of the process instead of the whole process, and that's what's fatal here. If I change 1 byte here, it only changes 1 byte there. Now, suppose this is the plain text. The plain text was padded. So that last byte is a number like 01, 02, 03 up to 10 if you use that PKCS number 7 padding. So if you consider it, there are going to be 2 values of this that will decode into valid output. If you don't change it and leave it in the original form, then you'll get the original plain text. And there's another one. If I change it to a value so this turns into a 01, then the padding will be valid again. 01 is an acceptable padding. So all I have to do, I know what the original value was of the ciphertext. All I have to do is change values until I find a value that no longer gives me a padding error. And that means I know this byte is 01. That's the essence of the padding oracle attack. Try all possible values. One of them is going to create a padding of 01. Now you determine this byte here of this intermediate value. And you can now move to the left and do the next one. Now that you know that one, you can change this byte and get that. You can eventually determine this entire intermediate value. And then once you have that, you can forge plain text. You can now put in ciphertext here, which when XOR'd with that will turn into anything you want. So I can take, I don't have the key, but I can forge ciphertext that will decrypt and say anything I want. So I can trick the system into thinking I know the key when I don't have the key. That's the version of this attack we're going to use. And that's the game. You can forge this plain text to say anything you want, as long as you're willing to do collateral damage and turn this into random garbage. So I can trick the system. All right. And I don't think I'm going to bother with this stuff. I just mentioned before, we had big arguments in one of my previous classes about the NSA, and here's a video that talks about it. And this is what I mentioned before. What the NSA's official goal is to have no bus, nobody but us. They want to have a system that they can get in, but nobody else can get in, and that relies on them keeping secrets. And the problem is, of course, they can't keep secrets worth a damn. Edward Snowden showed it leaked out, and the WannaCry attack showed it leaked out. So if the NSA has a secret backdoor into all the encryption, they don't seem to keep it secret very well. In fact, almost everything the NSA does is destroyed if they can't keep their secrets. And, that's why the crypto wars consist of people really being worried about the NSA. By the way, the NSA does good things too. When the NSA, first they weakened DES. Originally it was a 128-bit key, but they showed it to 56 so they could break in. But they also strengthened it. They improved the S box for AES. They did it making sure it would resist differential cryptanalysis, which was a secret technique. So sometimes when the NIST makes recommendations, they're actually making things stronger based on their classified information. So sometimes they're good, sometimes they're bad. Anyway, let's try another Cahoot, which is going to be here. All right. And here. All right. All right. coming in. All right. All right, so which system exposes AES to timing attacks? The table-based one, because I think looking up the 0th element of a table is faster than looking up the other elements. That's algorithmic. So all right, so which system is vulnerable to padding oracle? That's cipher block chaining. Taking one block as the initialization vector for the next block sounded like a bad idea, and it turned out to be a bad idea. Which system requires special processor instructions? That's the native instructions. Good. All right, what system leaves your penguin visible when you're encrypting an image? All right, that's the electronic codebook that encrypts each block separately. All right, and which system converts AES into a stream cipher? Now take counter mode, lets you create a pseudo-random stream of bits as long as you want. And CCSF rules is 1 twice. And push C. All right. Good. All right, I'm going to stop the recording.